and welcome to a standalone video on the fundamental theorem of arithmetic. In this video, I'm going to prove the fundamental theorem of arithmetic, which says that every integer greater than 0 has a unique prime factorization. And what that means is it can be written as the product of primes in a unique way. So this proof is going to be split into two parts, both of which will be in this video. The first part is going to be proving that there is a prime factorization of any integer greater than 1. And then the second part is going to be proving that there cannot be two different prime factorizations of the same number, which will mean every number has a unique prime factorization. So the easier part is proving that every number has a prime factorization. So how we're going to do this is so first to define prime factorization more rigorously. A prime factorization, it's a product. It's basically a list of some primes, or it's basically taking a number and turning it into the product of some prime numbers. So also the prime factorization of a prime number is just that prime number. That's how we're going to define it. So the prime factorization of 7 is 7 because 7 is a prime number. Also, just super quick recap: a prime number is a number that is not divisible by any other number except for itself and 1. And that number has to be greater than 1. And that's the definition of prime number. So 7's prime factorization would be 7. The prime factorization of 12 would be 2 times 2 times 3, and the prime factorization of 86 is 2 times 43. Okay. So first we're going to prove that there is a prime factorization. And we're going to do this basically, I forget, proof by induction. Yeah, that's what it's called. Okay, so what we do, proof by contradiction. You can do it either way, whatever. So say that there is a smallest number, that does not have a prime factorization, and we'll call this number n. Okay. So I'm gonna write this down, n. So assume n is the smallest number that does not have a prime factorization. Right there. That's number. Okay. Then we're gonna ask ourselves a simple question: is n prime or is n composite? Well, if n is prime, that's impossible because a prime number itself is just its prime factorization. For instance, 23 is a prime number, and 23 is just its prime factorization. Okay, so if it was prime, it would have a prime factorization. So therefore, it can't be prime because we know it doesn't have a prime factorization. If a number is not prime and it's bigger than 1, which we're basically assuming n is, then it must be composite. And a composite number means it's the product of two smaller numbers, neither of which are 1. Oh, I guess it doesn't matter. So now we know n is a product of two smaller numbers. Okay, so let's call those smaller numbers x and y. Okay, I was going to use a and b, except later I'm going to use that. I don't want to get people confused. Okay, so that means n is the product of two numbers x and y, both of which are smaller than n. And because they're smaller than n, and n is the smallest number that does not have a prime factorization, that means both x and y have a prime factorization, which means that they're the product of some primes. And because of this, that means that so I'm going to give an example. So say x is 2 times 3, and y is 2 times 7 times 11. Okay, these are two possible prime factorizations. So what I'm going to do is, that means n does have a prime factorization because it's just written right here. So basically, now going to that was me trying to give an example. Okay, so basically what I'm saying is, we know x and y must have a prime factorization, meaning that n has a prime factorization, and that prime factorization is namely the prime factorization of x times the prime factorization of y. As you can see here, n's prime factorization, if this is x and this is y, is 2 times 2 times 3 times 2 times 7 times 11, meaning it's a representative product of primes. And we have reached contradiction because n did not have a prime factorization, but we just found one. So therefore, there cannot exist a number that has that doesn't have a prime factorization. Okay, so we have now completed the first part of the proof, proving that every number has at least one prime factorization. Now we will prove that no number can have two prime factorizations. Okay, so we're going to use the number n again. So that was the first part. It was relatively easy compared to the next part. The next part is still doable though, so don't worry. So I think thanks for 10 subscribers. I think I have 10 subscribers now. Thanks. Okay, so yeah. So now what we're gonna do is we're going to go to the next part and assume that n is it doesn't even have to be smallest anymore. N is a number that has two prime factorizations. Okay. So what that means is n is the product of some prime numbers to different powers. How should I do this? Well, let's say there's basically a few ways to do this. It's sort of hard to represent. To write it down, it doesn't really matter. But basically, if I have two different prime factorizations of the same number, what that means is because they're different, they must disagree in one place. Maybe, and what that would look like is, say I had some number that was 3 times 3 times 7. That was one of the prime factorizations. And it also had the prime factorization 5 times 11 times 23, okay? Now, obviously, if you check these out, they're not the same. But for the sake of example, maybe there'll be some that are the same. So let's go along with this. So basically, what we have now is we have, like, here. So they must disagree in one spot, at least one. So right here, we see this has 3's in it, and this does not. What? So, and another example to show you that they will always disagree in one spot. If one of our prime factorizations was 3 times 7 and the other was 3 times 11 or whatever, again, note that the prime factorization must differ because this will have 2 3's in prime factorization, this will have 1 3. So what this means is if I have any two prime factorizations of the same number, by definition of them being different, there must be at least one prime that appears a different number of times in each of them. Okay, so let's say that prime number appears A times in the first one and B times in the second. Also note that later I'm going to be using the numbers A or the letters A and B. That's going to be a separate meaning. But for now, I'll just say it appears A times in our first prime factorization and B times in the second, and those are different numbers. Meaning, say, without loss of generality, that A is smaller than B, then what we can do is we can remove, we can basically divide by that prime to the power of A, which essentially removes A copies of that prime from each of the prime factorizations. Okay, so now we have two prime factorizations that are equal, one of which has no primes, none of this specific prime we've talked about in it, and then the other one has at least one of those. So basically what we've done is we said if there's, just to recap, if there's two prime factorizations, then at least, and they're different, then it means that there must be something in them that appears a different number of times. So basically we divide out that thing until it appears no times in one and at least once in the other. Okay, so if it appears 5 times here and 6 times here, we divide by that prime to the power of 5, so now it'll appear no times here and 1 time here. And so yeah, that's what we've tried to do so far. So now what we're going to do is, we know it does not appear in here in this prime factorization. It appears at least once in this prime factorization. Now by the definition of divisibility, or virtually the definition of divisibility, what that means is that this is divisible by that prime. From now on, I'm going to call that prime P. P is the prime we're talking about. And because these are equivalent, obviously, if this one's divisible by P, then this one's divisible by P. So now we're just going to focus on this one, okay? So we know this is divisible by P because we just talked about that. And we also know this is the product of primes, none of which are P, because we removed all the primes, all the copies of P from it. Okay, so yeah. Okay, so now we have a product of primes, none of which are P, and we're going to simplify it a little bit further before we go to the final step. So let's say, alright, so what we have is some. I'm gonna call each of these primes K1, K2, K3, etc. Okay. Yeah. So this is our prime factorization we're talking about. right here. K1, K2, K3. Okay. Oh wait, I wrote on the wrong side of the page. I already had stuff written there. Yeah. Oh, okay. So etc. And this is a prime factorization for some prime numbers K1, K2, K3. Okay. So, and we know that this is divisible by P. Now we also know that the Ki is not divisible, or that is not equal to P for any Ki. So what we're gonna do is we're gonna look at the sequence K1, K1 times K2, K1 times K2 times K3, and then like K1 times K2 times K3 times K4 until we get to so let's say there's in primes in the factorization, so it goes up to K in. Now I've already used the in before, so I'm going to use K im. Let's say there's in primes in it. So, and we're going to keep on doing this until we get up to okay, so just to recap, what I know is I have this this product of primes, K1 times K2 times K3, all the way up to K im, and it is divisible by P. None of these numbers are P. So now I'm going to write this list of numbers K1, K1 times K2, K1 times K2 times K3, K1 times K2 times K3 times K4. Try saying that 10 times fast. And then, I'm not going to read that out loud, but same idea, except now we go up to Km. Okay, so now we have, as we look, is K1 divisible by P? Alright, so the answer is no. And the reason for this is because K1 is a prime that is not equal to P, and the only divisors of a prime are itself and 1. So therefore, P does not divide this number, okay? So we could write a little X next to this, okay? So no, it does not. Alright, so now we ask the question, does K1 times K2, is that divisible by P? And, there's two ways to do this proof depending on which order you choose to do stuff in. Either is fine, but I'm doing this order, whatever. Maybe it was a tiny bit better, though. It doesn't matter, whatever. So we ask this question, and I don't know. The answer could be no, it could be yes. Okay? And we ask the question here and here. At the very end, we know the answer is yes because, remember, we talked about how this is divisible by P. So we can put a check mark here. So now for some super duper complex calculus, trigonometry, complex analysis, Taylor's... No, I'm kidding. This is super easy. So we know there's an X here and a check mark here. That means, and that represents whether or not it's divisible by P. So that means at some point it must jump from an X to a check mark, okay? So if I have a list, eventually it's going to have to stop being an X and go to a check mark, which means there must be some point on this list where one of the things is an X and then the next one is a check mark, okay? Now let us just focus on this point for a second. And I can write this down. Say this happens at like the ith one, okay, where it goes up to Ki. So say like K1, K2, K3, up to Ki minus 1. This, I'm going to put an X, and then K1, K2, K3, up to Ki, I'm going to put a check mark. So basically what we have here is we know it's an X, and here's a check mark. Somewhere in between it has to switch. Let's say that happens at the ith one. So it goes from this to this. So then what happens here is, I've just written down here. Okay, so we know this must appear somewhere for some. Okay, so we know that this number here is not divisible by P. We know that this number here is divisible by P. And we know that basically by definition of this X and check mark that represent whether or not it's divisible by P. And then we know what the difference between these is. We're multiplying this by Ki to get that. And this is very important. Ki is not divisible by P because K is a prime. Remember, all these numbers are primes. This is prime factorization. And none of these primes are equal to P. And if a prime is not equal to P, then it's not divisible by P because a prime is only divisible by itself and 1. And P is neither itself nor 1. So it follows by that. Okay. Okay, so therefore, I'm going to write... So basically we have this number, which is not divisible by P, multiplied by Ki, which is not divisible by P. I'm not going to write that down, or not for now, is equal to this, which is divisible by P. So let's call those... So we have some numbers A and B, such that A is not divisible by P, and B is also not divisible by P, but the product is divisible by P, okay? Alright, so So right here we have P does not divide A, P does not divide B, but P divides AB. Also, I think earlier. Oh no, that's why I used X, Y instead of A, B, because down here I knew I was going to be using A and B. Okay. So now for the coolest part, in my opinion, of the thing. Okay, we're gonna look at the multiples of B. Okay. So what this means is I'm gonna write down the multiples of B. So we have 0, B, 2B, 3B, etc. Okay. Well, these are the multiples of B. Okay, and we're gonna look at you don't have to do remainders, I was planning on, but you can just do. We're gonna look at whether or not these numbers are divisible by P. Okay. So we put a check mark earlier before we were doing check marks if it's divisible by P and X's if it's not. Same thing here. A little different because we're using different numbers, but here a check mark if it is divisible by P, and an X if it is not divisible by P. So 0 is obviously divisible by P, following from the definition of divisibility, namely that if you divide it, you get an integer. So we put a check mark there, okay? Now, so we have a check mark by 0, because 0 is obviously divisible by P. Then B is not divisible by P, because right here I wrote P. Oh, sorry, I didn't explain this notation. This means P does not divide A, P does not divide B, and P does divide A times B. So right here I know P does not divide B, which means that I can put an X by B, okay? Alright, so let's see. Now what we do is we look for the first multiple of B, besides for 0, which is divisible by P, okay? And let's call that K, okay? So let's say we go on and we get to a multiple, and this, remember, we're defining K as the first multiple, alright? Okay. So what that means is we have some number KB, and this is the first multiple, besides for 0, of B that is divisible by P, okay? Alright, so now, to give you an idea of what we're about to prove, I'm going to prove, and we're heading towards a proof by contradiction, but basically I'm going to prove that basically only multiples of K can times B can be divisible by P. I said that badly. You'll get the idea once I get into it. All right. So now what we're gonna do is we're gonna look at alright. So and also note that it's K must be larger or equal to 2 because we're looking for the first one bigger than 0, and we said it. So that means it has to be 1 or bigger. It can't be 1 because we know B isn't divisible by P. So therefore, it must K. I'm gonna write K is larger or equal to 2. Okay. All right. So now what we know is I'm gonna draw X's up until here. Okay. Because none of the multiples of B before KB are divisible by P, and this follows from the definition that we define KB as the first multiple of B that is not divisible. Or that is divisible by P, sorry. Okay, so now we're going to look at K plus 1 times B, okay? And I guess there's multiple ways of looking at this. You know, they both work. I just want to do it a slightly different way. Let's say we have some number L times B, okay? And we want to check if this is divisible by P, okay? So we want to check if this is divisible by P or not, okay? So what we're going to do is we are going to basically... So let's say L's remainder. So basically, we are going to look at the remainder of L when you divide by K. So we're gonna say that L is equal to some number times K. Let's say J. So JK. Just kidding. Plus some number C. Okay, where C is the remainder. So what we have is for some given number L times LB, we're trying to determine whether or not this is divisible by K, okay? Again, accidental pun because I said okay and we're talking about K. Whatever. Anyway, so LB, we're trying to figure out whether or not this is divisible by P. I might have said it's divisible by K earlier, sorry. Alright, so what this means is we're basically seeing what its remainder is, alright? So say it's basically remainder is C, that means you can write it like this, by definition of remainder basically, which means L times B would follow to be Also note that that c must be smaller than k because it's the remainders, what you have left when you can't take away any more k's. Okay, so then multiplying by b, we get lb is jkb plus, yeah, yeah, that's good. But plus cb. Okay, this is by definition of multiplying things. Alright, so now we want to see, is this divisible by p or not? Okay. Well, we know that this is divisible by p because look right there. I said so. We defined it as the first multiple. Also, I guess that would be important. Well, I'll get back to it in like 30 seconds. Well, that must be funny. I was like, it's important, and then I'm like, I'll get back to that. But don't worry, it's fine. Okay, so then obviously this is divisible by p. So it's basically, so basically we want to know, is this divisible by p? Because obviously, something that's divisible by p plus another thing that's divisible by p is divisible by p, which would mean that this is divisible by p. And if this isn't divisible by p, what that means is that this isn't divisible by p, so it's not. And that follows from basically you can add together remainders. Okay. So basically, what we want to do is CB basically divisible by p, and that is equivalent to our question. Well, let's see here. All right, so CB. Well, C is a remainder of L when you divide by K. Okay, meaning that C is smaller than K because it's the remainder. Okay, so it's some number between 0 and K minus 1. Okay, so we want to figure out if CB is divisible by P. That's what we're curious about. So this is the key part here. Right, CB is a multiple of B on here, smaller than KB, because CB or C is smaller than K because it's the remainder. And because we define this as the first check mark in between here, it must not be. So therefore, it can't be unless it's 0. So therefore, if LB is divisible by P, that means C must be 0. Otherwise, this would not be divisible by P, and this would. So that means the sum would not. So if this is if a multiple of B is divisible by P, it must be a multiple of K. Okay, so like L must be a multiple of K. And now I'm not sure. Maybe you can see the proof coming up, but here we have. How do I want to go for this? Yeah, that'll work fine. Okay, so let's look at some multiple or just some numbers that are divisible by P. So it is obvious-ish. I don't want to say that if you don't find it obvious, but whatever. It is not super difficult-ish that P divides P times B because it's a multiple of P. PB is a multiple of P. So basically, P divides P times B, okay? And also P divides A times B because I've written it up here, right here, okay? Okay, so therefore we know that, and because of what we described down here, where L, if this is divisible by P, L must be a multiple of K, we know both P and A are multiples of K, okay? So now let's see. So we know P is a multiple of K, which means K divides P. So what numbers divide P? Well, 1 and P. So K could either be 1 or it could be P. But as I've written conveniently right here, K cannot be 1 because it has to be bigger than or equal to 2. So therefore, K must be P. Okay? And what this means is that, but then the other value, we just said that because P divides AB and the thing we wrote down here, K must divide A, and if K is P, that means P must divide A. But that's impossible because right here I've written it doesn't divide A. So we have reached a contradiction. And remember, our original assumption was saying that there were 2 prime factorizations to the same number in. Okay, so what we have done is we have shown that if there was the smallest number that did not have a prime factorization, and this is a recap of everything we did, then you could find 2 small factors, and then you could get a prime factorization from that. And then we showed if there were 2 identical ones, that would mean you could basically, they would have a different power. You could divide by the power. This one wouldn't have any in it. This one would, meaning that this is divisible by that prime, none of which are in its prime factorization, which means basically by going 1 by 1 through the primes in it, you would get to a point where jumped, meaning that now you have 2 numbers A and B, and this is just super recap. It's harder to understand this way if I'm doing it fast. A and B, neither of which are divisible by P. They're the products are divisible by P, and we look at the first multiple of B, which is divisible by P, and we see that both A and P have to be multiples of that. We also know that that multiple cannot be 1 because P is a multiple of that. It means it must be P, which means A is a multiple of P, which is a contradiction. So therefore, we have proved the fundamental theorem of arithmetic. QED. Thanks for watching. Smash that like button. No, I'm kidding. Thanks.